All right, so this week we're taking a deep dive into geometric transformations. From classical conversations, the math map, and I know some parents might feel a little overwhelmed when they first see this material,
Yeah.
but believe me, we're going to break it down, and by the end of this, you'll feel totally prepared to teach this to your homeschoolers.
And the really cool thing about transformations is that they're not just some abstract math concept. We see them everywhere, literally all around us all the time.
Okay, so before we jump into the specifics, what is a transformation? I sometimes get lost in the terminology.
It's actually much simpler than it sounds. Imagine you're rearranging your furniture in your living room. You're moving things around, right?
Yeah.
You might flip a chair or rotate a bookshelf. That, in essence, is a transformation, a change in the position, the size, or the orientation of a shape.
So we're basically giving shapes a makeover. The math map focuses on four main types of transformations: translations, reflections, rotations, and dilations. Do we see all of those equally in, say, real-world design?
Well, they all play a role, but you'll definitely see some more than others. Let's start with translations because those are probably the most straightforward. It's simply sliding a shape from one place to another without changing its size or orientation.
Oh, like when you see a repeating pattern on a building, or like a border,
Those decorative borders, you often see those on buildings.
like a frieze pattern.
Yeah, those repeating patterns.
We have one on our fireplace mantle.
There you go. And it's fascinating, isn't it, how math is just woven into art and architecture.
It is. So that's translations. What about reflections?
Reflections are like looking in a mirror. You're flipping a shape over a line, creating a mirror image. Think of a butterfly. Its wings are a perfect example of reflectional symmetry in nature.
So rotations are like spinning a wheel.
Turning a shape around a fixed point, called the center of rotation, the hands on a clock face.
Okay, I'm with you. I think I'm good with translations, reflections, rotations.
Yeah.
But dilations,
Dilations can seem tricky at first, but they're really about changing the size of a shape. You're either making it bigger or smaller while keeping the basic shape the same. Think about zooming in or out on a picture on your phone. That's a dilation in action.
so for dilations, are there like specific rules about how the size changes? Like, is it always double the size? Or can it be any amount?
That's a great question. Dilations use what we call a scale factor to determine how much the size changes. If the scale factor is greater than 1, the shape gets bigger.
Okay,
If it's between 0 and 1, it shrinks.
so it's like a multiplier, kind of.
Exactly. Now, here's an important distinction. Translations, reflections, and rotations, those are all what we call isometries. Isometries preserve the size and shape of
Yeah.
the original figure. But dilations change the size, so they're not isometry.
Okay, that's a good distinction. So with these four transformations, translations, reflections, rotations, and dilations, I mean, are some used more often than others?
Well, they all have their place, but I think it helps to look at some real world examples to really see how they work. We've talked about those frieze patterns with translations, right? But think about something like a blueprint for a house.
Okay.
You might need to translate the image of a window to different locations on the plan. Or in graphic design, you could use translations to move elements around on a page.
Yeah.
Reflections, those are really crucial in things like engineering and architecture because symmetry is often essential for stability and for aesthetics, how things look. Rotations are super important in physics and astronomy.
Yeah.
When we talk about the Earth rotating on its axis, or the planets orbiting the sun, and dilations, well, they are essential for things like maps, scaling images. Even understanding how our eyes perceive depth involves dilations.
Wow. So they really are everywhere when you start to think about it.
They really are. It's amazing. And the more you start to recognize these patterns, the more you'll start to see them everywhere.
So we've got a good sense now of what each transformation is
Yeah.
conceptually, but how do we actually describe them mathematically? Like if I wanted to explain to my kids exactly how a shape has been translated, what would I say?
Well, that's where things get a little more technical. But don't worry, it's still very manageable. In geometry, we often use what's called coordinate notation to describe these transformations. It's like a set of instructions that tells you exactly how to move each point of a shape.
So it's like a secret code for each transformation.
Exactly. It's like a secret code. And once you crack the code, you can transform any shape you want.
This is pretty cool.
Yeah.
It does make it a lot more fun when you can tie these abstract ideas to real world things.
Oh, absolutely. And speaking of real-world examples, have you ever noticed the beautiful symmetry in snowflakes?
Oh, yeah.
That's all thanks to rotations and reflection.
I never really thought about it that way before. That's true.
yeah.
They're so symmetrical. Okay, so before we go on to how these work on a graph.
Mm.
What's the most important thing for our kids to kind of grasp at this stage?
I think the key is to start with a solid understanding of what each transformation does visually. So they really need to be able to picture it.
Yeah.
You know,
Yeah.
picture a translation, a reflection, a rotation, a dilation.
So lots of hands-on activity, maybe using manipulative or even just having them draw their own transformation.
Don't be afraid to use everyday objects to kind of illustrate these concepts. And once they have that foundation, you can gradually start introducing the more formal mathematical language and notation.
All right, so we've talked about the 4 types of transformations and get some great ideas for teaching them in a hands-on way.
Mm-hmm.
What about when we take it to that coordinate plane? That's where it starts to feel a little bit more abstract. For me, anyway.
I understand. But it really doesn't have to be intimidating. Just think of the coordinate plane as a map, right? Each point on that plane has its own unique address. So when we apply transformations, we're essentially just changing the address of each point.
So we're giving those points new coordinates.
Exactly,
Okay.
based on what type of transformation we're doing. And what's really neat is that each transformation has its own set of rules, almost like a formula for how those coordinates change.
Let's break that down a little bit for each one.
Mhm.
So let's say we're doing a translation. How would that affect the coordinates of a point?
Well, with the translation, remember, we're just sliding that shape around without changing its size or orientation.
Yeah.
So on the coordinate plane, a translation is going to shift all the points of a shape by the same amount, either horizontally, vertically, or both.
So if we wanted to move a shape, say 3 units to the right, how would that change the coordinates?
A perfect example. To move a point 3 units to the right, we would simply add 3 to the x-coordinate of that point. So if our original point was, let's say, 2, 5, the new point after the translation would be 5, 5. What about reflections? Are those more complex?
They are a bit trickier, but still totally manageable. Remember, reflections are like flipping a shape over a line, creating that mirror image. And on the coordinate plane, we usually reflect over the x-axis or the y-axis. Each of those lines has its own rule for how it affects the coordinates of a point. Let's take the x-axis as an example. So if we reflected a point over the x-axis, how would the coordinates change?
So we're basically using those lines as our mirror. If you reflect over the x-axis, the x-coordinate actually stays the same.
I'm feeling better about reflections. How about rotations? How do those work on the coordinate plane?
Rotations on the coordinate plane can be a little more complex, involving some trigonometry. But for now, I'd say just focus on understanding the visual concept of turning a shape around that fixed point. The math map introduces rotations about the origin, which is 0.
So we're spinning it around the very center of the coordinate plane.
And the most common rotations are 90 degrees, 180 degrees, and 270 degrees, either clockwise or counterclockwise.
So at this point, for teaching our kids, it's probably best to just start with visual examples of those rotations. Maybe use tracing paper or some cutout shapes.
Absolutely.
And then if they're ready for it, we can get into the specific coordinate rules later on.
That's a great approach. Visualizing those rotations is key to understanding how they work.
All right, we've done translations, reflections, rotations. Now dilations on the coordinate plane. What about those?
Dilations on the coordinate plane are all about multiplying the coordinates of a point by the scale factor.
Okay, so can you give us an example of that?
Sure. Let's say we have our point 2, 5 again, and we want to dilate it by a scale factor of 2. We would multiply both the x and the y coordinates by 2.
So our new point would be 4, 10.
And remember, if that scale factor is greater than 1, the shape gets bigger. If it's between 0 and 1, it shrinks.
I'm seeing kind of a pattern here that each transformation has its own rule for how it affects those coordinates, but it's all based on simple arithmetic, adding, subtracting, multiplying.
Once you understand those basic rules, you can apply them to any point on the coordinate plane. And now you're equipped to pass on that code to your homeschoolers.
This is so helpful. It's making me feel so much more confident.
I'm so glad to hear that. Remember, you don't have to be a math expert to teach this. You just need to understand the basic concepts and be able to explain them clearly and in an engaging way.
Yeah. And you're giving us so much to think about. Is there anything else that we should keep in mind as we're teaching this to our kids?
I think one of the most important things is to emphasize that transformations are not just some abstract mathematical idea, but a way of describing the movement and change that we see all around us, like the patterns in nature, the designs we create.
Before we wrap up transformations, I wanted to touch on something you mentioned earlier, which is parent functions. I know those are really important in algebra, but how do they connect to transformations?
Parent functions are like the basic building blocks of all other functions. They're the simplest versions of each type of function. like a straight line for linear functions or a parabola for quadratic functions.
So they're kind of like the starting point for understanding all the more complicated functions.
When we apply transformations to parent functions, we can see how those transformations actually affect the shape and position of the graph.
So by understanding how transformations affect parent functions, we can predict how they'll affect any function.
Precisely. It's all about recognizing those patterns and applying the rule.
This is great. I feel like I have a much deeper understanding of transformations now, and I'm really excited to share that with my kids.
And remember, the Math Map provides tons of practice problems and examples to help solidify those concepts.
It really is a great resource.
Yeah,
Well, I think we've covered a lot of ground today in our deep dive into transformations.
it all ties together.
It does. Well, I'm feeling so much more confident about tackling this math map material this week. Well, to all of our listeners out there, you can do this. Embrace the challenge, have fun with it, and enjoy the journey of learning alongside your homeschoolers. Until next time.